Okay, shall we start? Let's go to continue to explain the isoparametric representation and some more things. And just to make some context, you remember we started talking about the element representation talking about the linear triangle element, which is a very simple element which allows us to explain all the features necessary to calculate the stiffness matrix and the consistent nodal vector using the variational formulation we presented the second day, departing from the total potential energy principle. First I said that this linear triangle element is a simple element. Just to explain, it's a particular case where we find a closed form expression for the stiffness matrix. So this is very easy to calculate. But if we want to extend these calculations to a much more complex element, we find lots of problems, like the completeness requirement for convergence. Trying to find the shape functions for this completeness condition, it's difficult, and the integration of the stiffness matrix is difficult as well, because we're going to find very complex expressions. So we have answered to these 2 points using this isoparametric representation and the numerical integration of the stiffness matrix. Okay. Last day I presented this isoparametric formulation for the quadrilateral elements. Now we're going to talk about triangular elements from a general point of view, not only the linear triangle element, the easy linear triangle element at the beginning, but any triangular elements, isoparametric triangular elements. And we're going to apply the same method, same steps we were talking about last day for this isoparametric representation from quadrilaterals. Remember that at the beginning, in the first slide with the linear triangular element, we were talking about these triangular coordinates. It's a geometric issue from the triangular element. And we found that these triangular coordinates were used as shape functions to interpolate the geometry and the displacement, which is our primary variable. So we have 2 interpolation variables using these shape functions and E. But at the beginning, these triangular coordinates were only a geometric definition for every point of the triangle. But then, in the isoparametric representation, in a general point of view, we are talking about these natural coordinates. So we are not talking about these triangular coordinates anymore, but natural coordinates from this general point of view for any isoparametric representation of any element, quadrilateral or triangular. So these natural coordinates lead us to a shape functions definition expressed in these natural coordinates, taking into account only the geometry of the element and not this location in the domain. So these shape functions were defined to interpolate the geometry and to interpolate the displacement, which is the objective, the primary value of our problem. This geometry is used in the integration step, and the displacement interpolation is used to express this displacement function using these nodal points to find the continuum function using this finite number of interpolation points placed in the nodes of the elements. So this is the general scheme for the isoparametric representation, and the only change with respect to this previous slide is the concept of natural coordinates that now we are using in a general way. Of course, as we told last day, this scheme is perfectly extendable to the 3D problem, just taking into account the z coordinate besides of apart from the x and y coordinates in the plane problem. So this is the scheme we use for the quadrilateral elements, and we talk about how to find the shape functions using the line dot product and the steps to get to the stiffness matrix and the consistent nodal vector. And now we are going to do the same using this for these triangular elements, all the triangular elements, any of it, not only the linear one. So to remember that the isoparametric representation is characterized by this geometric interpolation using these shape functions. First of all, we have these consistency conditions, so all the shape functions must sum 1, and these two summation operators are the interpolation of the geometry, so we use the coordinates of the nodal coordinates x and y to get the interpolation of the any point x and y above all the geometry of the element, in this case the triangle. That was the plane stress element. So we are talking about the 2D representation, and the displacement interpolation again is based in the interpolation of the continuum function using these nodal values ux and ue and these shape functions to define this overall displacement function over the element. If we explain these summation operators in matrix form, we find again the typical isoparametric representation considering this consistency condition, 2 rows for the geometric interpolation and 2 rows for the primary variable interpolation, which is the displacement. Again, if we are talking about the structural problem, we talk about displacement function, but we could be treating a thermal problem or another different problem, so our primary variable would change, but the step and the method is the same. So what happens with our linear triangular element characterized by the nodal values in 3 nodes in the corners? So here we have the information of the geometry, the coordinates, and the displacement nodal values. We want to interpolate everything using these values, and we find that the natural shape functions to interpolate geometry and displacement are the natural coordinates. Remember, these natural coordinates were defined as 1 in the corresponding node and 0 in the opposite side. So we have as many shape functions and triangular coordinates as nodes, 3 in this case. So imagine that we have a linear evolution from this opposite side to the corresponding node for shape function 1. We could have shape function 2 and shape function 3 as the triangular coordinates, and we would have quite similar linear evolution from the corresponding node to the opposite side. So this is our shape functions and the plot of one of them, and 3 and the other 2 are quite similar. So finally, the isoparametric representation for this triangular element would be this matrix form, and these are the 3 shape functions as we treated in the first time we talked about this linear triangle. But now the point is, what happens if we are trying to work with a quadratic triangle? Well, this is a bit more complicated, but now we have the steps, we have the method to get these shape functions, and we expect that this quadratic triangle is characterized by these 6 nodes, 3 of them in the corners of the triangle, and 3 of them in the midpoints of the triangle. So now, to get these shape functions here in, again, the isoparametric representation, in this case we have 6 nodes, so we have 6 columns and 5 rows here, consistency, 2 for geometry and 2 for the displacement. These 6 shape functions are calculated again using the same idea as we use in the quadrilateral elements, which is we have 6 nodes, so 6 shape functions, 1 per node, and for this node we have a corner node and corner shape function which must be 1 in this node 1 and 0 in the other 5 nodes. Remember that our triangular coordinate G1, this node, is 1 here and 0 in the opposite side, and same thing with this node 2, which its triangular coordinate is 1 in this node 2 and 0 in the opposite side. So for example, if we want to calculate this shape function, we must banish this function in these 3 nodes, and we get it using these triangular coordinates. So G1 is 1 here and 0 here. That's why our shape function for the node 1 involves this term here, G1, which is 0 here and 1 here. So we banish these 3 nodes. Now we must do the same with these 2 nodes 4 and 6. These nodes here has got a value for this G1 coordinate, which is 1/2. Remember that this triangular coordinate is 0 here, 1 here, and its evolution is from this point to this point, taking into account that this from these midpoints 4 and 6, the shape function got 1/2 value. So this T1 less 1/2 banishes these 2 points here, 4 and 6, and we get, so T1 times T1 less 1/2 is our shape function, which banishes these 5 points. But now we must use a normalization factor for this node, because we want the shape function to get one value in this node. So we need 2 normalization factor in this shape function. So now for this node we get a 1 here, this expression here. So the idea is the same idea we used in the equilateral elements, that's banishing the shape functions in the opposite sides, and using this idea we get the functions with the shape functions for these 3 corner nodes in this way, using just the shape function, the corresponding function to the node in this way. So these 3 expressions are similar, and for the midpoints here, this point here, 4, we must banish this side, but these 2 sides, look at point that this node 4 is between node 1 and node 2, so the triangular coordinate 1 vanishes in this opposite side, the triangular coordinate T2 vanishes in this opposite side. So for this node 4, its corresponding shape function involves these 2 coordinates, these 2 triangular coordinates T1 and T2, because it vanishes the opposite sides, which includes the 5 nodes where we want the function to be 0. And now we need a normalization factor 4 to get a 1 here, because this is 1/2 for coordinate T1 and 1/2 for coordinate T2. So we must multiply by 4 to get the 1 here in this node. So using the idea of banishing the other nodes using these triangular coordinates, we get this shape function for the corner nodes and the midpoint nodes in this way. So we don't have to solve any system equation, we just use the line dot product to get easily these shape functions. So we have 2 different types of shape functions for the corner nodes and the midpoint nodes, and here we can see a representation of these 2 different shape functions in the corner nodes with this evolution 1 here and 0 in the other nodes, and this midpoint with this 1 value here and this evolution in the rest of the element, of the triangular element. This is for quadratic triangle. So using the same idea, this isoparametric representation, we get to the shape functions expressed in these natural coordinates, now natural coordinates. So we are able to represent geometry and displacement, and in fact this geometry can be represented when the triangle gets to this shape, this curvilinear shape in the 3 sides. So now we are able to work with all these kind of geometric triangles. Okay. Later we will see that this curvilinear geometry and this sort of strange triangles can lead us to some problems with the Jacobian matrix. But now these shape functions allowed us to represent this geometry as the convex or not convex curved sides, and even we can work with this triangle, which, imagine here we have a curved side. This curved side is easily represented by these 3 nodes. So these 3 nodes represent this curved side in the geometry. Here we have as well these 3 nodes to represent a straight side. So these 3 nodes are able to interpolate a curved side and a curved displacement function. So, but the sides are straight here, so this is what we call a superparametric element, because the geometry is over represented. So we have too many nodes to represent a straight side. So this is what we call a superparametric element, and the other ones are isoparametric elements because the geometry and the displacements are represented in the same way. So in fact, for this triangle, we don't need so many nodes in this side to represent the geometry, a straight geometry, but sometimes we use it. Okay, so now same thing with the quadrilateral elements in the isoparametric representation. To get the integral to find the stiffness matrix, we use numerical integration and Gauss integration rules. So now for the triangle we have different Gauss integration rules, different from the ones used in the quadrilateral elements. We must compute the Jacobian and the shape functions with the partial derivatives with respect to these Cartesian coordinates. So this is what we are going to do in the triangular case using these quadratures. Remember that the Gauss-Legendre quadratures used in the quadrilaterals now use different quadratures depending on the location of the integration points. This is the simplest integration rule, the centroid rule. We use 1 point. That's 1 degree interpolation for the polynomial function. So we have the triangle, we have the area, we calculate the area, and this integration is calculated like 1 divided by area integral of the function, any function. Now we are going to define this function, but any function is integrated depending on these triangular coordinates or natural coordinates, like the value of this function at this centroid point, 1/3 and 1/3 and 1/3, which are the three triangular coordinates of the centroid of the triangle. This assures us a 1 degree polynomial interpolation for the primary variable, for the integration. But we have much more alternatives for this numerical integration, like the 3-point integration. And in case of this 3-point integration, which assures us this 2-degree polynomial integration, we can find two different Gauss quadratures depending on the location of the points. They could be in the interior of the triangle, or they can be in the sides of the triangle, in the midpoint sides of the triangle. So we are going to talk about these open rules, open quadrature rules, and these closed rules for integration depending on the location of the points. But anyway, we have 3 points. The expression for the numerical integration for this function f is 1/3 of the function placed in these 3 points characterized by the natural coordinates 2/3, 1/6, and 1/6, and this weight 1/3 for all the 3 terms. So these are 3 points located in the interior of the triangle, and this midpoint rule again considers 3 points of integration, so guarantees 2 degree of polynomial integration. But now the location of these integration points are in the midpoints, so the natural coordinates involves 1, 2, 1/2, 1/2, and 0 for all of them, and this weight is again 1/3, 1/3, and 1/3 for the 3 terms of the numerical integration. Well, these integration points, as we did in the triangle, in the quadrilateral elements, are located in this way. So it's our work to decide which is our integration rule, which is the degree of exact integration we want, and which is the computational cost of using 1, 3, or 6 or 7 integration points for any case. This is the first centroid quadrature, where the location of the integration point is here in the centroid of the triangle. This is the weight, so we have a weight of 1. Yes, we must evaluate the function in this centroid value. Here we have the 3 points quadrature, so we have 3 points in the interior of the triangle and 3 points in the boundaries, placed in the midpoints of the 3 sides. This is an open quadrature, this is a closed quadrature. In some problems we have to choose which one of them is recommendable, is good for our problem. For example, in the next slides we are going to see, we are going to talk about the difference between this open and closed quadratures, because sometimes if we want to calculate the location of this point here in the boundaries, we could have some problems. Okay? And apart from that, we have these open quadratures with the location of these Gauss integration points inside the triangle, with 6 or 7 Gauss integration points, which is more as this degree 4, degree 5 of polynomial exact integration. Usually, when we work with a linear triangle or triangles elements, we use this 3 points integration rule, or even sometimes with this, for very simple problems, with this 1 point of integration rule here in the centroid. But usually we have these 3 integration points as the most useful for our integration problems. Okay, so now numerical integration is takes place using the same idea, the same double summatory with the weights and with the evaluation of the f function using the strain displacement matrix, the elastic matrix, and the Jacobian value. All of them are evaluated in the natural coordinates, so we must make a change of variable using the Jacobian matrix, using the partial derivatives of the Cartesian variables, as we have seen with the quadrilateral elements and in the general theory. So one last detail is that we've been talking about these triangular coordinates of the triangle, but in fact they are related using a consistency condition. So we've been talking about G1, G2, and G3 natural coordinates, okay? But in fact, they must assume 3, so we could express one of them, for example, G3, using this expression here, 1 less G less eta. So in fact, we could represent these natural coordinates using the same natural coordinates as in the quadrilateral elements called G and eta. So we can identify G with G1, eta with G2, and express all the locations, all the coordinates for all the points in the element using this G and eta, taking into account that the third coordinate is just a linear function of these two. So we could express everything we have said using just G and eta. So imagine for this number, for this node 1, this is G equal to 1, this is G equal to 0 in the opposite side. For this node 2, this is eta equal to 1, and this opposite side is eta equal to 0. And here, this node 3, we could talk about 1 less G, 1 less eta value, which must be 1 here because G and eta is 0, because they are 0 in this side and this side. And this value, 1 less G less eta, must be 0 here, because the sum of these two natural coordinates is 1 in this side, so this third coordinate is 0, it vanishes here in the opposite side. So this is another way to express these natural coordinates, much more similar, or clearly easy to identify with the quadrilateral elements. So we must express everything we have said using just this G and eta natural coordinates, which makes it a bit more easy to understand. So you can choose these natural coordinates, these 3 natural coordinates, or these 2, just to represent the isoparametric triangular elements. So if we do this, if we choose these natural coordinates, the rest, all the formulation, all the integrals, and all the development is exactly the same we have presented in quadrilateral elements. Okay? And I think this is everything to say about triangular elements, linear and quadratic and whatever triangular elements from the isoparametric point of view. So we can forget the first development, and now we can treat the linear triangular and the quadratic triangular element as we did with the quadrilateral elements, following the same scheme to get to the shape functions expressions and the stiffness and consistent nodal vector and matrix to solve our problem. Okay. Is there any question until now? Any problem? Any question? Any detail? It's not clear. Because now, if not, I want to present a very specific problem which is quite useful in structural analysis, that are the structures of revolution. In fact, we have been talking about the plane stress. We have talked a bit about the plane stress just to say that plane stress in fact is a very similar problem like as plane stress, so it's a question of changing some mechanical parameters to treat the plane stress like the plane strain. So for us, as a concept is the same, and for implementation in a computer is more or less the same, plane stress and plane stress. In fact, you implement just one of them, plane stress usually, and you change the parameters, and you don't make two implementations. Well, there is another interpretation of that two-dimensional problem, which are the structures of revolution. So structures of revolution are quite useful in structural engineering, because sometimes we must treat with pipes, for example, or tubes, or mechanical engines, jet engines, for example, columns. There are lots of structures which has this axisymmetric geometry distribution. So for structural analysis, sometimes we can model a problem using this revolution formula structure, this axisymmetric formulation. Well, sometimes we can make a global analysis of the problem using this axisymmetric, and just afterwards make a local study of the elements. And sometimes it's the opposite. We can make a global analysis of the problem using a 3D formulation, and some of the elements could be studied using this axisymmetric formulation. So sometimes, to simplify the problem, to get to a good approach of the results, we can use this axisymmetric formulation, which is in fact a bidimensional problem. We are going to treat as a bidimensional problem. We're going to see that in fact it's a particular case of a plane strain problem. Okay. So let's see. These structures of revolution are produced when you have a cross section and you generate this structure by moving around an axial axis over 360 degrees around it. So when you have this geometry, this axial geometry, your problem involves this axial geometry, you can treat it using only this cross section. You can analyze only this cross section if you are able to impose the proper axial conditions. Okay. So this is useful because many things in structural engineering involve these revolution bodies, because they are easy to manufacture than much more complex geometries. Besides, these revolution bodies have an optimal strength, optimal strength-weight ratio because of the distribution of the particles. Okay. And sometimes these structures of revolution are used as a structure, like a column, for example, and sometimes as a shelter, as a container for something, which is quite usual in structural analysis. So it's not strange that you find something that you can simplify using this cross section, which involves much less computational cost than a 3D simulation of the whole body, the whole revolution body, and you can find similar conclusions or proper conclusions just simulating this cross section and extending the results and the conclusions to the whole body. Okay, so let's consider this revolution structure, this axisymmetric problem. Let's go to define it. It's not only a question of geometry, because we must assure that the response, the behavior, the final behavior of the structure must be axisymmetric. So it's not only the geometry involved, but the loads must be as well axisymmetric as well. So the cases of loading we can consider is a distributed load in the radial direction. So imagine this is our structure and this is our radial load. Okay? We call it FR in this horizontal plane. This is normal plane to the axial, to this axis. We can have a vertical load in an axisymmetric distribution. So imagine a vertical load around this circle or this line. We can have a distributed load over this surface, or we can line load over this line, this boundary. So this is a vertical load or parallel load to the axis, and this axisymmetric distribution of vertical load make our problem again see axisymmetric. So we will find an axisymmetric behavior, and this allow us to treat the problem as a structure of revolution. And again, it's not finished, because we can have a point load like this one here acting in the axis. So this point load we allow us to treat the problem as an axisymmetric problem. And imagine that we have a punctual load which is not placed in the axis. If it's so, we could employ a mathematical trick, which is express this non-axisymmetric load using a Fourier development, and then superpose the results obtained for any of these harmonic components. So even if the punctual load is, if the point load is not in the axis, we could treat this axisymmetric problem, this non-axisymmetric problem, as if it was, using this Fourier development. So this is the set of axisymmetric loads we can have in this axisymmetric problem, just to consider it as if it is. If it's not, we could simplify or just treat it as a 3D problem anyway. But we're going to consider these three kind of loads in this development. Because of the axisymmetric distribution of the particles and loads, we're going to consider this coordinate system, this cylindrical coordinate system, where the coordinates are r, the distance of the point from this axis, this z coordinate, which is, in this case, is the vertical coordinate, but in fact is the coordinate in the direction of the axis, and this circumferential coordinate, which is the angle from an arbitrary origin, what you want. This is the angle which locates the point in the structure, in the cross section. So every point in the cross section is defined using these three cylindrical coordinates. Of course, our structural magnitudes, strains and stresses, are expressed in this axisymmetric problem, taking into account that they must respect this axisymmetric distribution. So we will have this radial component, or this radial component, same thing, for the stresses and for the strains. We have this vertical or axial component for the stresses and for the strains. We have this circumferential component for the stresses and for the strains. We call it sigma or E sub theta. And for distortions, we are going to consider this distortion Rz and this distortion Rz, which are in equilibrium in this common site, and the distortions in this direction, the distortions R theta and Z theta, so the distortions left, they must vanish to keep this axisymmetric distribution. So in our problem, these two distortions, the ones which involves the circumferential component, vanishes, they are considered as 0, because we must respect this axisymmetric problem. So in the axisymmetric problem we will have these 4 components. These 4 components for stresses and strains. Remember that in plane stress and plane strain we had just 3. So in fact we have this sigma and strain, this circumferential component extra, apart from the 3 typical from plane and plane stress and plane strain. This circumferential component from stress and strain, it's a difference between this plane strain and this plane stress problem. In fact, this is due to the axisymmetric distribution, because in plane stress or plane strain, a radial displacement or a horizontal displacement is in fact a rigid body motion. But now, if we consider this radial displacement here, this radial displacement must be extendable, must be extended around the axis. So if we have this displacement, this radial displacement, at the same time we are generating a circumferential strain due to this. This is explained in this scheme here. So imagine that we are in this point, we have a radial displacement. The radial displacement makes that this line is bigger here. So now we can consider which is the strain in the circumferential direction. We have a radial strain and stress, of course, but now we have a line which is bigger, larger than before, so we can calculate this circumferential strain like the difference between the initial and the final length of this line. This is the final length and this is the initial length, taking into account that we are placed in the RP position. This is the radius of the initial position, and divided by initial length, so we get an expression for this circumferential component like the displacement, radial displacement, divided by the value of r, which is the position, the initial position of our point. So this is the extra component from the plane and stress and plane strain. We call it the circumferential strain and stress, or the hoop strain or stress, which is quite different from the ones we've been treating before in the bidimensional problems. Take into account that this circumferential strain involves a radius, an r, a radius, location of the point, which means they does not involve partial derivatives as it used to be with the radial and the vertical strains and the distortions. So we are not using a partial derivative, it's just a displacement divided by r. Besides this r, this radius is placed before this is divided by r, so we must be very careful about what happens when this r, this radius, is 0. So we will have some problems here in the axis where r is 0 when we calculate this circumferential stress, and we're going to see what happens with this extra component. In fact, which is interesting from these structures of revolution is the treatment of this circumferential component using this radial displacement. This is the difference between the plane stress and plane strain. In fact, we can talk about this axisymmetric problem as a limit case of the plane strain. So imagine our plane strain with the axis moving to the infinite. That means that this r is tending to infinite. So in this extreme, this limit case of plane strain of axisymmetric point, we would obtain a plane strain problem. Okay. So then, which are our degrees of freedom, and just to get the stiffness matrix and the stresses and the consistent nodal vector, again same thing, but in this revolution axisymmetric problem, our degrees of freedom are this displacement, but now they are radial and vertical displacement. In fact, radial and parallel to the axis displacement, let's call it UR and UZ. they are depending only depending on the radius and z coordinate. So the axisymmetric distribution of the particles lead us to a non-dependent displacement of the circumferential component. So theta here vanishes. So we have two displacements depending on r and z. In the 3D problem, the strain tensor has these 9 different components, in fact 6 independent components, but now in our axisymmetric problem, these distortions relating to zeta vanishes, so we have only these 4 or 5, in fact 4 independent components, these 3 strains, this circumferential stress and this distortion in Rz. So we place this strain tensor considering the non-zero components using this 4-component vector here with the strains and the distortion here. Look that this circumferential component is placed in the third place. Remember, this is our extra guessed in the problem from the bidimensional problem. And the stresses, we could say something similar. The stresses in a 3-dimensional problem involve this stress tensor with 9 components, in fact 9 non-zero components, but 6 of them independent. But in our axisymmetric problem, we have these tangential stresses which vanishes. So we have 5 components, 4 of them independent, because these distortions are equal. And we place these 4 independent components in this 4-component vector involving these non-zero components of the problem. So 4 strain components, 4 stress components, all of them depending on these 2 degrees of freedom displacement. And now we are going to the strain displacement relations. They are known, but we calculate them in the cylindrical coordinates system. This strain, this radial strain and this vertical strain are the partial derivatives of the displacement. The distortion again is the partial derivative of these 2 components with respect to the opposite. So partial derivative of displacement r with respect to z, and same thing with displacement z with respect to r. This is the total distortion. Remember that in the tensor we don't place this value of the distortion, but the value of the distortion divided by 2. So the tensor component ERZ is the distortion divided by 2. This is the one which is in the tensor, but the total distortion is calculated in this way. Careful with these 2. And our extra component, which is the circumferential strain due to this radial displacement divided by r. So as I said before, this radial strain does not involve this partial derivative. Remember that this partial derivative affects to the interpolation of the displacement using the shape functions. So this changed quite a bit our formulation and our way to treat this axisymmetric problem using the shape function, as we are going to see. These kinematic relations, these strain displacement relations, in matrix form are expressed in this way. This is our partial derivative operator, which relates the 2 displacement component and this 4 strain component. And now the relation between strains and stresses is this elastic matrix here. This elastic matrix again, this elastic matrix again involves this 4 by 4 matrix, taking into account that this circumferential component and this distortion, which is related directly to this tangential component. And for an isotropic material, we have this strain, this elastic matrix relation between strain and stresses. Remember that this is the factor used in plane strain, so the matrix in plane strain is like that, but we have added 1 row for the circumferential component for the stress and strain. So this component is the relation between tangential stress and distortion. These are the two relation components for radial and vertical, and this rho related the circumferential stress and the circumferential strain here in our problem. Now we got to the equilibrium equations, which in the three-dimensional problem and in cylindrical coordinates show these three equations here, which involves, of course, the stresses, radial stresses, tangential, circumferential stresses, and the body forces. Of course, we are considering three components, radial, z, and circumferential component. But now, this is a general three-dimensional problem, but expressed in cylindrical coordinates. For an axisymmetric problem, we have this tangential component, which involves the circumferential component, which vanishes because we have assumed that they are 0. So this is 0, this is 0, and this is 0 again. So these tangential components vanishes, so they simplify our equilibrium expressions, especially in this third equation, equilibrium equation, where this component vanishes, this tangential component vanishes, and this is a circumferential stress which remains constant with respect to this circumferential component. So we can't have a variation of this sigma with respect to the circumferential component, because the axisymmetry would not accomplish in this case. So this sigma theta depends on r or depends on z, but does not depend on this component. So this partial derivative again vanishes, and same thing with this body force component in the circumferential direction. So this third equation in fact vanishes because it's 0 equal to 0, and we keep these two first equilibrium equations, which are the ones that govern our axisymmetric problem, involving the radial component of the stress, the tangential stress Rz, and the body forces in radial direction and vertical direction, and this vertical stress here. So this is the two equilibrium equations used in the axisymmetric problem, which simplifies the 3D problem. So this is the one, this is the point, because we want to simplify and we got to calculate a much more simple problem using this axisymmetric formulation. So now that we have the degrees of freedom and the expression for strains and for stress and the elastic matrix, so we have the ingredients for apply the total potential energy functional, and to minimize this functional, we can express, remember that this is the point, we can express the internal energy and the external work depending on this primary variable, which are the displacement. Here we have the displacement, and we have seen before, this is 1/2 of the integral of this product between stresses and strains. This stress is, we can express it as the elastic matrix times the strain tensor. So this is the integral for the internal energy. Remember that this is a matrix which involves these two values. In fact, these two values and these two values are 0 again if the material is isotropic, and we want to calculate this integral over the volume of the structure. Take into account that we are integrating in the whole volume, so the axisymmetric volume, not only the cross section, but the axisymmetric volume of the structure, which is the one we are interested in. I put this label here because now we want to assure that this integral, we are able to calculate it. And remember that this circumferential component involves radial displacement divided by r. if we divide by r, we must be careful what happens in the nodes in the axis, because there the value of the radial component is 0. Okay? Now we are going to see what happens. This is for the internal energy, and the external work is calculated considering the body forces, external work, and the boundary tractions, external work. So these two components can be calculated using this general expression: body forces times the displacement, and the tractions times the displacement. This is integrated over the volume, and this is integrated over the boundary tractions domain. So here we have this body forces in radial and vertical component, not the circumferential one. This is the displacement, and these are the tractions, again in the radial direction and vertical direction, not in the circumferential direction, times the displacement, the 2 degrees of freedom, the displacement we are considering in our axisymmetric problem. And now we can calculate this total potential energy using this expression, the internal energy less the external work, and this will lead us to the stiffness matrix. So now this is for a continuum problem. We are now in the continuum space. We must remember that our real structure is a 3D structure with an axisymmetric, with an axial symmetry. So this is our cross section. Now we are going to discretize our domain, and what we are going to do is to discretize the cross section, only the cross section, and treat the problem as an axisymmetric problem using elements, triangular elements or quadrilateral elements, which in fact represent this what we call ring finite elements. So this triangle is representing all these ring elements of volume, although we are treating the element, the finite element, with considering this the area and these 3 or 6 interpolating nodes of the triangle, but we don't have to forget that in fact we are calculating this volume. So to make these integrals, we apply what we call this dimensionality reduction. So we want to reduce the 3D problem to a 2D problem, considering this calculation of the volume around the axis. So this differential of volume here is calculated like 2p times the radius times the differential of area. This differential of area is inside the cross section, and this radius is calculated for every point. So our internal energy now is calculated like 1/2. This integral involves this differential of volume. This 2p goes outside, and we find this radius here for any point of the triangle, any point of the cross section area, which generates the axisymmetric problem. So we have a very similar integral as we had in the plane stress and plane strain problem, but we have now this r here, which changes quite a lot the expression of the integral we are going to calculate. Same thing with this external work. The external work is 2p integration of these body forces, of the external work of the body forces, times the radius. So this dimensionality reduction leads us to a differential of area to work in the cross section, where we pay a price in some way, because we must add this radius, this r component, radial component, for every point of the integral. This is if we work with this element of volume. So we are extending in a radial, moving around the axis, the plane element. So we are getting, in fact, this differential of volume. We are building volumes around the axial, around the axis, but some of the boundary tractions could be applied in the surface or even in a line. So the external work is calculated like 2p integral of this boundary forces times the displacement around the area, and this area, this differential of area, is calculated in this way, is expressed like 2pr. This r is the location of the point, and this is differential of the length where the load is applied. So our integral is expressed in this way. So we find another 2p factor out of the integral. Again, the radius of this point, every point of the domain, and this differential of s is the length where the load is acting. So we must make an integral over the line where the load is applied. So we change our element of volume by elements of area, and we've changed our element of surface where the load is applied by elements of length elements, or length, just this length where the load is applied, to reduce the dimension of the problem from 3D to 2D, to implement this formulation in a finite element code. In fact, what we are doing is trying to minimize the total potential energy, which is the difference between this internal energy and the external work. So we are minimizing a total potential energy, and this minimization leads us to an expression which is equal to 0. So as it says here, the implementation usually banishes this 2p factor because it appears in all of the quantities, in all of the expressions involved in the total potential energy, less one particular case. So body forces involves 2p factor in this dimensionality reduction. The boundary attractions, again, if they are in an axisymmetric distribution. But we have another case we've been talking about some slides ago, which is the punctual load. This punctual load here, it does not act over an axisymmetric surface or volume like the body force of the attraction. So the external work due to the distributed loads with an axisymmetric distribution, in radial case, in the vertical case, we easily calculate the external work, assuming that the external work is calculated like the load times the displacement, and we have a 2p extension around the axis and the radial component for any point of the domain. So for us it's no problem because we treat it like this, using the expression in the slide before. But when we have an external point load in the axis, so we have some small problem, because in the dimensionality reduction we don't have a 2pr extension of this load, because the load is only f times the displacement. This is the external work due to the point load acting in the axis. So usually what we have is to fit this this load using this trick. So divide the punctual load times the 2p, we multiply the same thing. So we consider this load, this point load, divided by 2p for the external work, and then assuming this value for this point load, we can banish this 2p factor in all the terms and treat it this way. So usually FEM implementations banishes this 2p factor in the calculation, but considering that if point loads acting in the X exist, we must make this little change in the formulation of the external work and then in the consistent nodal vector. Taking into account all of this, now we have all the ingredients to calculate this stiffness matrix and this consistent nodal vector for this Iso-P parametric element with n nodes. That was for the continuum problem. Now we want to use an isoparametric element, in this case axisymmetric element. So again, for an axisymmetric, for an isoparametric representation, we have this relation between the geometry displacement and the shape functions. These shape functions is something about the element, so don't worry about these shape functions. Any element we are going to use in the cross section has these shape functions, as we have been explaining before. So the strain displacement equations now are this partial derivative operator we have presented some slides before. We have n nodes, so we will have n shape functions. We are going to place them in this way. It's not the only way to define this shape function matrix n, but using this distribution of the shape functions, we can calculate this strain displacement matrix P using this differential operator and this shape function matrix, and we're going to find these three values distributed in this way: this vector, radial, vertical, and this circumferential component, and these two related to the distortions. Any of them are calculated using these partial derivatives. So we want to calculate the partial derivative with respect to r, with respect to z, for these two values, radial and vertical, these q values. Remember that our shape functions are expressed in natural coordinates. So again, we have the same problem. We want to calculate the partial derivative with respect to radial and vertical, that's cylindrical coordinates, but we have this n e expressed in natural coordinates, so we must calculate the Jacobian matrix to find the relation, the partial derivative of the natural coordinates with respect to the Cartesian or cylindrical coordinates. And again, important thing, here we have this vector which involves the circumferential component. Remember that this circumferential component does not imply a partial derivative, because it is 1 divided by radius times the shape function interpolation of the displacement. So now this value here, this B matrix, which multiplies the displacement component, involves the shape functions, not the partial derivative, but the shape functions divided by r. So again, we have with a problem with this r, which is dividing here, and if we want to calculate this value, this vector here, we must be careful with the value of r in the axis, because there the value of r is 0. So we must apply numerical quadratures that does not imply that the Gauss integration points are placed in the axis. We can, from this expression here, we can obtain an expression for the stiffness matrix. If we consider this elasticity matrix, we multiply this elasticity matrix times the P displacement matrix P, and again this they multiply by P displacement matrix transpose, and we will find this matrix here, which is the one which is inside the integral, with these expressions here. Okay, these four expressions are calculated using these q vectors and these c constants calculated in this way. But the point is that usually we use numerical integration using these Gauss rules integration for our elements. So we can use triangular elements with the Gauss integration rules we have seen some minutes before. We can use quadrilateral elements using the Gauss integration rules for quadrilateral elements. But the point is that now our integration, our stiffness matrix, is calculated like an integral of this function here, which involves, first of all, 2 dimensions, and P, number of integration points in the 2 dimensions, could be different to 2 dimensions, but usually we use the same P number of Gauss integration points. We use these 2 weights, which are associated to any integration point depending on the quadrature we are using. This strain displacement matrix here, which is depends on the natural coordinates, as we have seen in the slide before. This is elastic matrix, at first it is constant. Again, this B strain displacement matrix, which in general depends on the natural coordinates, and this is something which is different, because now we must integrate this radial coordinate, which we can interpolate using the interpolation of the geometry. So this radial coordinate is again calculated using the geometric interpolation, using the coordinates, the nodal values of the geometry, and the same shape functions, again, depending on the element we are using. And due to the change of the variable from the Cartesian from the cylindrical, in fact, to the natural coordinates, we can calculate this Jacobian, which involves the partial derivatives of the cylindrical coordinates with respect to the natural ones. Okay, so this term here, this r, which is the special guest in this development, involves first of all an geometric interpolation which changes the order of the polynomial we were used to work using triangular or quadrilateral elements. So now we must think about which is the quadratures we want to use, because now the order of the polynomial, the order of this function changes because of the appearance of this r here. Besides, we have another problem. Here we have the expression for the interpolation of this radial coordinate using these radial values of the nodes, of course, of the element, whatever. The same function, again, depending on these natural coordinates. So this is placed here. So for every point, for every Gauss integration point, we want to calculate this r, and we are going to do it in this way. So imagine that we have this n shape function here, which changes the level, the order of this polynomial expression inside the integral. And besides, we have a small problem again, because inside this p-strain displacement matrix we have this vector here, these expressions here. In general, we will have a shape function divided by r. So if we try to calculate this stiffness matrix using numerical Gauss integration points, sooner or later we will have to integrate this, calculate this expression here in the elements, quadrilateral, triangular, next to the axis. So we must be conscious that if an axis, if an element has one node or two nodes in the axis, and we use close numerical quadratures, we could find an integration point here with radial coordinate equal to 0. So we will be in trouble here, because this r is dividing in the circumferential component. So to calculate this stiffness matrix, usually we use this inferior point Gauss ruled integration just to solve this problem here, because of the appearance of this r, here in this term. So we usually use open for numerical quadratures to solve this problem and to get the stiffness matrix expression in the case of axisymmetric problem. This is for the stiffness matrix, and consistent nodal vector for forces, in the case for the body load, for the body forces, are calculated in this way. So we use the same expression. Now we have shape functions, matrix, this body force on this r, and again this r is the radius, this is the radial component of the point. We have this radial component because of the dimensionality reduction using this differential of volume, like 2p differential of area. Now here the 2p factor has been banished because we neglect this value, which appears everywhere. And this integration, this integral here, is calculated using numerical integration quadratures. And for example, for a quadrilateral element with p integration points, here, we use the same idea, the same development of the numerical quadratures. So we assume that in the two directions we have two summatory expressions with two weights, k and l, in the two directions. This is number of integration points. This could be different, but usually is the same. This is the shape function matrix depending on the natural coordinates. This is the body forces, again depending on the natural coordinates, so we must change this variable. That's why we use this Jacobian matrix, which again involves the partial derivatives with respect to the natural coordinates. That usually, in general, this is a matrix depending on the natural coordinates, and again we must calculate this radial coordinate. This radial coordinate is calculated using the geometric interpolation. This geometric interpolation is calculated using these shape functions, same shape functions that they used for the displacement component. So this geometric interpolation is again used here to calculate this value, taking into account that this summatory operator is calculated in the Gauss integration points here. These G and eta components are usually the location of the Gauss integration points for every Gauss integration point considering this double summation. So we find a stiffness matrix. We find a consistent nodal vector for body load, and same thing with the fractions. So now we have all the ingredients to solve the problem, to find our primary value in these nodes where the nodal values are placed. But now I have some different things in this axisymmetric development with respect to the plane stress and plane strain development, which is above all the appearance of this circumferential circumferential component here in B strain displacement matrix, and the appearance of this radial coordinate in the numerical integration. Consider that if the radial coordinate is dividing, now we have irrational integrals here, which makes it much more complex and which justifies a bit more the use of numerical integration. So to calculate in an analytic form this stiffness matrix will be too complex, so that's why we use this numerical integration using Gauss rules integration, and we define the number of Gauss integration points needed just to guarantee a certain degree of approximation of the numerical integration of the stiffness matrix and the consistent nodal vector. So now that was the development of the axisymmetric problem, sometimes quite useful, and I think with this structure of revolution we end the presentation of the p-dimensional problems. So now you are able to find all the ingredients in the plane stress and the plane strains and the axisymmetric problem just to solve a b-dimensional problem, which usually is used as an approximation of a 3D-dimensional problem, which is much less expensive to calculate, and which lead us to interesting conclusions about the whole behavior of this structure. Now we have solids. The solid formulation for the isoparametric representation, which is the following subject and the convergence requirements. And I prefer to leave the solid representation of the isoparametric representation of the solid elements and the convergence requirements for the next day. So I think we are going to finish now, unless you have any problem, any question, anything. Yeah.
Regarding to when the problem has a punctual load. So that means when we are modeling in plane strain, we apply the load. If the load is F, we must apply the load F divided by 2 pi.
In the implementation. So when you are implementing in the computer, you must consider point load divided by 2p. This is if you make this factor, when you make this dimensional reduction, you treat the problem as a 2D problem, and in this external work here, you have 2p, 2p, and 2p in the internal energy. Okay, so imagine that you don't have any punctual load. You can make this implementation. If you have these 2p everywhere, you can avoid this 2p multiplication in your computer because it has its cost. So you can avoid it. If you have this point load, you can treat this point load like this. So you can treat this point load as the value of the load divided by 2p. So now you can banish this 2p everywhere. Usually people don't want to make too much operations, so that's why this 2p is not calculated. But if you banish this 2p and you have this point load, you are in trouble. You're calculating something which is wrong, because you are assuming that this external work of this point load is not what it is. This is the external work. This is the external work. If you don't have this 2p factor here, you are assuming that your external work is the load times the displacement divided by 2p, which is not. Okay? So this is the point. Because this radial load is, you extend this load around the axis. Same thing with this vertical load, which is not here, but imagine that this is you have a vertical load which you must extend around the axis, but you don't extend this f. Okay? So if you don't take into account the 2p factor for all of them, you are cheating with this external work, because you in fact are calculating the external work divided by 2p. So that's why we make this trick. We change this point load by f divided by 2p, and now we neglect this 2p everywhere, and the result is not affected. It's a question of implementation. For example, if you are happy with the 2p, you can calculate this using the 2p, the external work of the body forces using the 2p, same thing with these boundary forces, and you can keep your point load with any change, without any change. If you are happy. But if you don't want, you are multiplying by 2p everywhere, so you are assuming a computational cost which maybe it's avoidable. It's only a question of implementation. What more? Yeah.
Question. It says that if you are in a nose around the axis, you will have a problem.
Yeah.
But I think actually, how to pass it in a
How to pass this problem? Well, the problem is that when you calculate this component here, let's see. The problem is that you have this component here divided by r. So if you place a 0 here, you are blowing up your solution. So you must calculate this without the 0. But you at the end, you calculate this in a numerical quadrature. So your problem is here. Your B matrix here, which involves this shape function divided by r. Okay, and which r you are calculating? Well, the location of your point comes here. So you are calculating this expression in the integration point. So if this integration point is placed in the axis, you will have an r equal to 0. So the solution for this problem is to use an open quadrature, which places the Gauss integration points not in the boundaries, but in the inferior. Okay? Well, there's another possibility, is that you calculate this integration not using a numerical integration, but you do it by hand. So imagine that you do it by hand. So sooner or later, you will have to integrate this divided by r, and you will have logarithm expressions or something like that. Okay. Well, there are expressions in the literature to calculate the integration, the analytic integration in the points in the axis, even in the points which are parallel to the axis, okay, where the difference between the radius is 0. Okay, but this is from analytical point of view. If you do it by hand, if you do it numerically, you try just to use Gauss integration points which are placed not in the axis but in the inferior of the element. Okay. What more? Any more questions? Well, there's a very interesting assignment related with this axisymmetric problem, which makes all of these things clear: the problem with the R, the problem with the axis, and so on, and the analytical expressions. So I expect you to do it, and this, I think, it will clarify everything about this axisymmetric problem, which we've been talking about this class. What more? More questions? More things? If not, we leave it here. Today, no rest, and we finish a bit earlier. In next class, we'll talk about the solid elements, the 3D elements, and the convergence requirements